In episode 78, titled Cloud Attack Patterns, Storage and Metadata, we're focusing on how data exposure and metadata access can enable takeover, even when the environment has no obvious vulnerable server to exploit. Cloud environments concentrate value in two places that are often underestimated: storage services that hold data at scale, and metadata services that provide runtime identity and configuration to workloads. If storage is exposed, attackers can learn secrets, internal architecture, customer data, or credentials that were never meant to leave the cloud. If metadata is reachable in the wrong ways, attackers can obtain temporary access tokens and use the cloud control plane legitimately, which can look like normal automation while still being hostile. These patterns matter because they are repeatable and high impact, and they often arise from configuration drift and unsafe defaults rather than from rare technical vulnerabilities. The goal in this episode is to understand how storage exposure happens, what metadata services do, why they are dangerous when unguarded, and how to validate and report findings safely without turning an assessment into a data leak event. Cloud attack reasoning stays calmer when you treat storage and metadata as first-class attack surfaces.
Cloud storage exposure patterns usually fall into a few predictable categories: public buckets, weak sharing controls, and mispermissions that grant broader access than intended. Public buckets are the headline case, where a storage container is readable by anyone on the internet due to permissive access policies or an unintended public setting.
Weak sharing can occur when objects are shared through broadly accessible links, long-lived share tokens, or overly broad access lists that were meant for a small audience but grew over time.
Mispermissions are a broader category, including policies that allow read or write access to many principals, or roles that have blanket permissions across storage resources. The risk is not only reading sensitive objects. Write permissions can be worse because they allow tampering, malware staging, or the planting of files that downstream systems trust. Storage exposure also shows up through indexing and listing permissions, where an attacker can enumerate what exists and then target the most valuable objects. In many real incidents, storage exposure is the earliest and easiest win because it requires no compromise of compute, only discovery of a misconfigured access control boundary.
The data impact of storage exposure is often immediate and painful because cloud storage tends to hold high-value information in concentrated form. Sensitive information leaks can include customer data, internal documents, source code, configuration files, backups, and logs that contain secrets. Once leaked, the problem is not just the immediate disclosure, it's the long tail of reuse risk, because exposed secrets can be used to access other systems long after the data was copied. Compliance consequences can be significant depending on what data is involved, because regulated data exposure can trigger mandatory reporting, contractual penalties, and long-term trust damage. Operational impact can also occur if storage is modified, such as when attackers delete or encrypt objects, disrupt pipelines, or poison data used by applications. The business story is often clearer than the technical story here. Public access to a data store is a direct breach risk. This is why storage misconfiguration typically ranks high in prioritization and remediation planning. Metadata services are the other half of this episode, and conceptually they are internal endpoints that reveal credentials and configuration to running workloads. In cloud environments, a workload often needs to learn information about itself, such as instance identity, role-based credentials, region, or configuration hints that help it fetch resources. Metadata services provide that information without requiring the workload to store long-lived credentials locally. The critical detail is that metadata is usually reachable through a special internal network address, and applications inside the workload can query it over HTTP-like calls. This design is convenient and powerful, but it assumes that only trusted code inside the workload will ask the metadata service for sensitive information. If an attacker can run code within the workload context or can cause the workload to make requests on the attacker's behalf, the metadata service can become a credential vending machine. In short, metadata services exist to enable secure automation, but they become dangerous when the boundary around who can query metadata is weak. Metadata is dangerous because it can provide temporary access tokens that grant real cloud permissions, often tied to a role assigned to the workload. Those tokens may be short-lived, but short-lived is still long enough for an attacker to list resources, read data, modify configuration, or pivot into more privileges if the role is overprivileged. Temporary tokens also often look like legitimate traffic because they are used through the normal cloud API, which can make detection harder if monitoring is not tuned for unusual patterns. The risk becomes more severe when the workload role has broad permissions, because the attacker's temporary access becomes a broad access key in practice. Metadata also reveals configuration details that can help attackers, such as network identity, service endpoints, and environmental context that makes later actions more targeted. The big exam-level takeaway is that metadata access is identity access, and identity access is control plane access. If you can get tokens, you can often do admin-like things without touching a traditional exploit chain. Common misconfigurations that enable metadata abuse often revolve around open network paths and unrestricted metadata access within workloads. Open paths can exist when network segmentation is weak, when workloads in shared networks can reach each other in unintended ways, or when routing allows unexpected access to internal service endpoints. Unrestricted metadata access appears when the environment does not enforce safeguards that limit who can query metadata or how metadata can be retrieved. Another common enabling condition is when applications accept user-controlled URLs or perform server-side fetch behavior, which can be chained into metadata access if the fetch can reach internal addresses. In that case, the attacker may not need code execution on the workload. They may only need the ability to influence a request that the workload makes. The broader pattern is that metadata becomes reachable from untrusted inputs or untrusted code paths, and that reachability transforms into token access. This is why defenders focus on hardening metadata access pathways and preventing workloads from being used as internal proxies. Now, consider a scenario where a workload can reach metadata endpoints unexpectedly, because it illustrates how easily this risk can arise. Imagine you are assessing a cloud-hosted application that processes user-supplied links or performs internal requests, and you discover that it can access an internal metadata endpoint that should have been isolated from that kind of request flow. The clue is that a request influenced by external input is able to reach an internal metadata service, which is not intended because metadata should be accessible only to trusted code for legitimate configuration needs. This scenario often appears when applications have URL fetch functionality, when network egress controls are permissive, or when internal routing allows access to special addresses without restriction. The consequence is that an attacker might be able to retrieve tokens or configuration information by causing the workload to query metadata and return the response. Even if the workload is otherwise secure, this reachability creates a powerful pivot because tokens obtained from metadata grant cloud API capabilities. This is why metadata exposure is often treated as a high-severity issue.
Safe validation in a metadata scenario means confirming reachability and token scope without abusive actions, because it is easy to cross a line from proof into exploitation. You confirm whether the workload can reach the metadata endpoint under the tested conditions, and you document the request path that makes it possible, such as a URL fetch feature or an internal request proxy behavior. If tokens are accessible, you focus on identifying their scope at a high level, such as what role they represent and what broad categories of actions they could allow, rather than using them to modify resources or access sensitive data. You avoid broad enumeration of cloud resources because that can create operational noise and may exceed what is necessary to justify remediation. The evidence you want is that metadata is reachable from an untrusted path and that the response contains credential-like material or sensitive configuration details. That is sufficient to prove the control failure and justify hardening without turning the engagement into an incident. Safe validation also includes immediate containment recommendations if exposure is confirmed because token access is urgent.
Mitigation concepts for storage and metadata focus on blocking unsafe access paths, using hardened settings, and monitoring for signs of abuse.
For metadata, blocking access means restricting which processes and request flows can reach metadata endpoints, and ensuring that user-influenced requests cannot target internal addresses.
Hardened settings include enforcing metadata protections that reduce exposure to request tricks and limiting token availability to trusted contexts. Monitoring is important because metadata abuse often precedes control plane activity, so watching for unusual token usage patterns, unusual role assumptions, and abnormal API calls can provide early detection. For storage, mitigation includes tightening public access controls, restricting sharing mechanisms, and enforcing least privilege policies so that roles can access only the buckets and objects they truly need. Safe defaults matter because many exposures happen when a bucket is created with permissive settings or when a sharing option is enabled temporarily and never revisited. The strongest mitigation posture is layered: prevent exposure, limit impact, and detect abuse quickly.
A common pitfall is assuming public access is intended without verifying ownership and scope, because some storage is intentionally public while other storage is accidentally public. If you treat every public bucket as a vulnerability without context, you risk misreporting and losing credibility, especially when a bucket is designed to host public assets like images or static files. The correct question is whether the access level matches the intended data classification and whether the exposed objects include anything sensitive. Another pitfall is ignoring write permissions, focusing only on read exposure, even though write exposure can enable tampering and downstream compromise. In metadata scenarios, a pitfall is overproving impact by using tokens to access sensitive resources, which can create unnecessary risk and exceed the safe proof objective. The professional approach is to confirm exposure and scope, then recommend controls that align access with intent. This keeps findings accurate and actionable.
Quick wins typically start with auditing public storage and enforcing safe defaults broadly, because those changes reduce the most common exposure paths quickly. Auditing means identifying which buckets or containers are public, which objects are shared, and whether any sensitive data is present, then closing unintended access. Enforcing safe defaults means preventing public access unless explicitly approved, using organization-wide policies that block risky configurations by default. Another quick win is tightening role permissions for storage access so that workloads cannot read or write broadly across many buckets. For metadata, quick wins include restricting internal request capabilities, preventing user-influenced fetch features from reaching internal addresses, and enforcing hardened metadata access settings that reduce token exposure. These changes are high leverage because they remove entire categories of easy attack paths without requiring application code changes in every case. When you implement these quick wins, you reduce both likelihood and blast radius quickly.
Reporting language should show the exposure condition, the accessible data or token risk, and the recommended safeguards clearly, because cloud findings can otherwise sound abstract. For storage, you describe what is exposed, such as a bucket being publicly readable or writable, what type of data is accessible, and why that exposure violates intended classification or policy. For metadata, You describe that the workload can reach metadata endpoints through an untrusted path. What kind of sensitive information is returned, and what role or token context is implied by that information? You recommend safeguards that match the issue, such as blocking internal address fetches, enforcing metadata access protections, tightening public access controls, and implementing organization-wide policies for safe defaults. You also note your validation boundaries, emphasizing that you confirmed exposure without performing disruptive actions or harvesting unnecessary data. Clear reporting builds trust because it ties a cloud configuration condition to a concrete risk outcome. It also speeds remediation because defenders can see exactly what to change.
To keep the key concepts sticky, use this memory phrase: storage exposure, metadata reach, token risk, fix.
Storage exposure reminds you that public or mispermissioned storage is a direct path to data leakage and tampering.
Metadata reach reminds you that internal metadata endpoints should not be reachable from untrusted paths or user-influenced requests. Token risk reminds you that metadata often yields temporary credentials that are still powerful and can enable control plane actions. Fix reminds you that the response is policy and configuration hardening, close public access, restrict roles, block unsafe metadata access, and monitor for anomalies. This phrase keeps your reasoning focused on the two main surfaces and the core outcome, unintended access that becomes broad capability. It also maps cleanly to mitigation priorities. To conclude episode 78, titled Cloud Attack Patterns, Storage and Metadata, remember that cloud compromise often accelerates when exposed storage leaks secrets or when metadata access provides tokens that enable control plane actions. Storage exposure is about who can read or write data, while metadata exposure is about who can obtain runtime identity and credentials from internal endpoints. Safe validation confirms reachability and scope without abusing access, and mitigation focuses on blocking unsafe paths, enforcing hardened defaults, and improving monitoring. If you had to implement one mitigation first, start by auditing and eliminating unintended public storage access because it is common, high impact, and often fixable quickly with policy and configuration changes.
Once storage exposure is controlled, you can then tighten metadata access paths and token hygiene to reduce takeover pathways even when workloads are compromised.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.